Hola, hola, hola. Buenos días a todos. Muchas gracias por vuestro interés en nuestro INRIA Chile Talk. Buenos días a los presentes y buenos días a los conectados, que sé que hay algunos conectados también. Bueno, hoy tengo el placer, ya no sé ni qué edición es esta de los INRIA Chile Talks, pero cada vez que lo hacemos es algo que nos interesa mucho. Estoy hablando en español, ¿está todo ok? ¿C'est bon? Eh,
Sí,
¿No?
sí, sí, bueno.
¿Sí? Bueno, esta edición, no sé qué edición es ya de los INRIA Chile Talks, pero desde que los venimos organizando es algo que ha suscitado bastante interés. Y tenemos hoy el privilegio de tener acá a Yannis Karmim. Yannis es investigador del grupo Almagnac en INRIA París. Y además de eso, tenemos un proyecto de colaboración desde el año pasado con el Grupo Almanac y además con la Universidad de Chile. Y estamos muy contentos de que además Yanis esté acá, pasando una estancia de 3 meses con nosotros,
Sí,
que está hasta aprendiendo español también.
poquito.
Pero más allá de eso, yo creo que la investigación que está haciendo Yanis en el contexto de este proyecto va a ser súper útil también dentro de la línea de evaluación de IA del Centro Binacional. Y bueno, más allá de eso, ya resultados promisorios que tienen que ver con la evaluación del contexto social y cultural latinoamericano, en particular dentro de los LLMs, ¿ya? Que existen acá. Así que es un placer para mí, Yanis, introducirte. Merci beaucoup.
Merci à toi.
Bon, c'est à toi maintenant. Ok?
Okay, so hello everyone. I will speak in English for clarity. So, as said, Nayat, I'm postdoc researcher at Almanac team, and my subject of postdoc is understand knowledge acquisition, and better inject new knowledge into large language models. So, why I did this talk? So primarily, I did not my PhD on large language model or NLP. I did my PhD on graph neural networks, graph theory, and I joined this amazing project between INRIA Paris and INRIA Chile. There was like this very good study between INRIA Chile and Université de Chile. The goal was to build an evaluation dataset to evaluate the knowledge of a large language model on LATAM culture. So I was a little bit disturbed because when this project was presented to me, they say that they will construct a question and answering based on Wikipedia. And for me, Wikipedia was on the training set of every large language models. So there was like contamination, and I had like a machine learning background. So when there is like the trained data in the test data, it's obvious that model will perform very well. So I was like surprised. But when we built this dataset on Wikipedia, the model wasn't that good. So it was a very big surprise for me. But I did a lot of research to understand why some knowledge are really well known by large language models and why some rare knowledge are not well acquired. Okay? So this talk is to share with you like all the research and all the answer of the question that I asked myself in the beginning of this postdoc. So let's go. So first, I want to remind a large language model if any have some question about it. So there is like 3 core components into large language models. I said that the first component is self-attention. It's a mechanism that allows a large language model to understand the connection between some words in a sequence. Also, self-attention mechanisms are inside the core architecture that is called transformer, that was popularized by Attention is All You Need in 2016. And of course, large language model, there is the word large. So we need a lot of computation, a lot of data, and the scaling law is the base of every large language model. So if you add a lot of data, a lot of parameters, and a lot of training resources, you will have better model. The transformer architecture are like the original one are built on an encoder and a decoder. The large language model are only decoder model. So the goal is to predict next token. So this is the core architecture of GPT, Llama, Olmo, and Gapron, which is the LLM of INRIA Almanac. So I made a little publicity about. And the goal of large language model during pre-training is to predict the next token. So a large language model will see a lot of data, like basically all the internet, and the goal is to reconstruct sentences. So for example, it will take like a Wikipedia article, and the goal is to reconstruct each word based on the context of the article. So by doing this, you maximize, like, for example, the probability, le temps est merveilleux, and you have to reconstruct aujourd'hui. And if you maximize this probability, the loss will decrease. You do that in a large amount of data, and you will have a model that understands well the language, the syntax, and also acquire some knowledge. There is like 3 big training steps into large language models. So the first step, which is like the more consuming in terms of resources and very difficult to do, is the pre-training step, because you will have like a lot of data, and this is the next token prediction task. But after that, you only have a model that is able to complete sentence. For example, you can't chat with him. It's just like a model that completes sentence. You can't give him instruction, for example, do me a summary, write me an email. He can't follow instruction. So there is this phase of training, which is called supervised tuning, instruction tuning, when you teach the model to follow instruction. For example, translate me this, write me an email, summarize me this text. And the big finding in these steps is you don't need a lot of data to do this. It was the finding of OpenAI in GPT-3 that language models are few-shot learners. So because of the ability of the pre-training task, it's more easy and you don't need a lot of data to follow instruction. After this, you have an alignment with human preference to teach the model to don't follow bad instruction, don't be hateful, don't give personal information, and so on. So the pre-training data. In the pre-training data, I said that there is like all of the web. You see Wikipedia, it's only 6 million documents, so it's very low compared to the other sources of data. And it's a very high quality of data because it has a neutral tonality. You have like articles in different language, so it's included in every data of large language models. And during pre-training data, pre-training step, the large language model will see a lot of knowledge. It will see that Paris, capital of France, are frequently associated. So he has the ability to memorize knowledge. So I define memorization as the ability to recover facts. For example, if I took the context, Paris is the capital of, if France is higher than other country in terms of probabilities, we say that this model acquires some knowledge. Okay? So let's go back in our LATAM culture. So we built this data set on Wikipedia, and me and Jamé as well, we say that, okay, the model will be like very good because Wikipedia is everywhere in the training data. So there is maybe like saturation in terms of performances, but we saw that So this is like Wikipedia in the dataset of Olmo, which is a popular large language model. And we saw that the performance wasn't that good on the LATAM culture. So even for big model like Mistral Large, there were only like 85%. So it's very low for MCQ datasets. MCQ datasets, it's multiple choice question answering. So it's very easy because you have like multiple choice, and it's more easy than give the exact answer with no context. So we saw that, and I was like really surprised that models weren't that good for answering questions about Wikipedia articles. So why that didn't work that well? Well, it's because large language models are not really database, you know? So in database, you will do like SQL query to get some information on the database. For example, if I ask what is the capital of France in a SQL code, it will say me Paris. If you ask something like this in a LLM, what is the capital of France? Well, it's a probabilistic model, so it will give you the most probable answer based on its intern probabilistic distribution. So it's very different. It's flexible because you can ask in a natural language, but it can also have, it can be inexact because it's probabilistic. So I think this question is very easy for all LLM, but if I ask very specific question like quand se déroule la fête de la quiche à Montigny-les-Metz, which is like a very small town, very small event and not really well known, well, the model have a lot of chance to give me a wrong answer. So there is like a disparity between popular knowledge and what we call long tail knowledge. So there is like this long tail curve you see in the left. You have like few events, few facts that are really popular, but you have like a lot of facts, for example, cultural things that are not really popular. And for example, in the LATAM culture on the internet, only 1.6% of cultural facts in the internet are about LATAM culture. So it explains, in part, the bad results of the LLM. It's because it will see like the cultural fact into Wikipedia, but not in other web pages or conversation, for example, in Reddit or something like that, compared to other culture like North America, Europe, and so on. So there is like a very strong challenges to understand how knowledge is acquired in a large language model. And I will give you like some of answers that I found in the literature, scientific literature, to understand this phenomenon. So we will see that exact memorization of fact does not mean that he can answer question about it. So it's very strange, but he can memorize, for example, the whole Wikipedia article perfectly, but not be able to answer simple question about it, because there is a distribution shift. So we will see also the knowledge storage capacity of LLM. So if LLM see like the entire internet, is it capable of like memorize it perfectly? The number of exposure, so how many times a knowledge have to be seen before the LLM memorize it. We will see also that inject new knowledge is very difficult, because when you inject new knowledge, you tend to forget the other one. So like a student, for example. And I will give you like a lot of training and usage tips for LLM. So let's go. So my talk is based on two works that are like really instructive, and I encourage to see it like deeply. So the first is the physics of LLM, which is a work done by Facebook to understand the core capacity of large language models, and also this paper, how do large language models acquire factual knowledge during pre-training. Okay? So let's go with physics of LLM. So the core idea of this study is to have control experiment. With large language model on the internet, for example, ChatGPT, etc., there is not a lot of transparency. You don't know on which data the LLM were trained, how many times, so you don't have like the exact data, the exact training. So it's very difficult to like experiment things and have like strong guarantee of what happened inside the LLM. So the goal of this study is to build like a fictional data set based on biography. So it's like synthetic biography of imaginary people. And they will train like a small model, a GPT-2, to see how many times the model must see a fact to memorize it, and a lot of experiments based on the knowledge. So now we have like a control setup with control data and a control setting, and we can like infer a new finding. Okay, so there is like 6 attributes in this biography, like the birth date, birth city, university, and they have like multiple templates, but it's all fixed. So every attribute appears in the same order. You will see that sometimes it can be, LLM is not that clever because sometimes it learns a wrong logic in the data, but the data set is constructed as it. And one of the first very interesting experiments is that exact memorization does not mean that the model is able to answer questions about this fact. So for example, they did a first experiment. They pre-trained the model with next token prediction on this biography of these n individuals. And then, so we have like the pre-training task. Then fine-tune to instruct the model to answer a question about these individuals on half of it. But when we test on the other half, 0% accuracy. So the model has perfect memorization, is able to reconstruct all the biography, is able to answer the question, the training question, but it's not able to answer question about individuals that were not in the fine-tuned dataset, because all the individuals are in the pre-trained dataset. Is that clear? If you have any question, don't hesitate during the talk. So there is like no knowledge extraction, and this is like the first finding. Knowledge extraction is different than memorization. So after that, they say, okay, we'll do a pre-training, but we will include in the pre-training task, so next token prediction, the biography, but also some question answering data. So it's not fine-tuning, it's pre-training, and then evaluate on the other half, and now you have extraction. So we saw like a lot of scandal in LLM because they were accused of putting evaluation data in the training set, and well, LLM are good in evaluation data because they saw evaluation-like data in the training set, during the pre-training set. So now, a mixed training, when you have like question answering style as well as the biography, you will have knowledge extraction, and it generalized to the n/2 individuals. It learns also very faster with this mixed training, so it's a good strategy if you want to train LLMs. The third result is if you don't have like question answering data, you can add diversity in your data set. For example, you will augment your data set with multiplicity, permutation, full name changes, and then when you do the fine-tuning, now you have generalization. So what does it mean? It's that you cannot just rely on memorization during your training. It's not a good signal. because you can have like good memorization, a very good base model, but that is not able to follow instruction because you didn't train well during this phase. Okay, so yes, this is like the key results of this first experiment. So now they did like a second pool of experiments, which is like really interesting. And these experiments focus on knowledge manipulation. For example, if I ask the model, does this person is older than this person? What is like the birth year of this person, even number or odd number, for example. An inverse search, for example, who is the person that was in this university and was born at this date, and how the model behave. So the first result that they show is without chain of thoughts. I will define chain of thoughts just the next slide. Without chain of thoughts, it's very hard to manipulate knowledge. For example, you ask, so they put this example, was Donald Trump born an even day? And no, Donald Trump wasn't born an even day. And then she asked him to, think. And yes, he corrected his answer. He saw that 9046 is an even number, so he said yes. But without chain of thoughts, she always give random answer about knowledge manipulation. So what is chain of thoughts? Chain of thoughts is like the model during inference that generates its own context to answer a question. For example, in DeepSeek, when I ask him to calculate the hypotenuse of a triangle, he generates context, and he used this context to answer a question. So this is chain of thoughts. So the first result, like very interesting, they also have like this biography dataset, but in the dataset, all dates are like full dates. For example, we have the date, the month, and the year. But if you ask him like only the year, he's not able to answer. So it's not really clever model, like at all. If you don't have diversity in data, he can't reason well during test time. So it was really surprising because he's able to give like the full date, but not just the year of the birth year. So after this, they test like classification. Some questions are here as examples, and also comparison. So was this person older than this person, etc. And what they found is without chain of thoughts, during the test phase, it's very hard to answer that kind of question. Basically, the model is completely random, and it's the case even for larger models because this is a Facebook team, so they test on Llama 30B, Llama 70B, etc. So what they found is that even if you fine-tune your model with chain of thoughts, so with like the complete reasoning, so for example, yes, this person was born in 2000, so 2000, it's an even number, so yes, it's an even number. So even if you fine-tune with this reasoning, the model is not able to answer during test time. It's only able to answer during test time if you add chain of thoughts. So chain of thoughts is another phase of training when you teach the model to reason. So not all models are able to do this. And the third result is that inverse search is impossible. So if you ask a model who was born at this date and was in this university, it's not able at all to answer it like they prove it. So for example, I test with Mistral, I ask who was born 26 January 47, and she gave me a wrong answer. It says Johnny Hallyday, but it's Michel Sardou. I use this because it's the same birthday, not 47, but the day and the month. But I asked GPT-5, and she was able to answer. So I was surprised, and they say in the dataset, in the paper, that if you inverse all the dataset, if you have like a lot of variation, you can have this kind of question. And of course, it's GPT-5. You don't know what it's inside, so maybe there is like a web search or something. But in the paper, they prove that it's like impossible to do it with that kind of data. Okay. So these are like the key results. And then they did like a third pool of experiments, and these are like very interesting because it was rely with our work of LATAM MCQ. So what is like the knowledge storage capacity of models? How quantity of information can large language model encode? And how many exposure to a fact a large language model needs. So they found that a large language model, when sufficiently trained, have the ability to encode like 2 bits per parameters. So for example, a 7B Olmo, which are like the smallest LLM available, and Gapron also as well, can store 40 bits of knowledge. So which is superior to English Wikipedia, for example. So even in small model, we have the theoretical capacity to store all Wikipedia. So it's a road for improvement, but it doesn't mean that you can manipulate and extract this knowledge easily. You have to find like training tricks to better extract this knowledge. So what happens if you have like a low exposure of a fact, for example, LATAM culture event? If you have like low exposure of a fact, you don't encode well the information, and they found that if you want to encode well a knowledge fact, you have to see it like around 1,000 times. So if a knowledge is not seen like 1,000 times, it's very difficult to extract it during test time. So it explains why the long tail entities are really hard to extract during test, and it's also very very bad because large language model does not encourage, does not preserve the diversity in the data, because they will always like generate the most probable, and they will like increase the probability of popular events and decrease the probability of rare events. And also what is like very interesting is that there is row of improvement, because they saw that if you change the architecture, you can increase this 2 bit per parameters storage. So maybe any question on this first part, or maybe I answer the question at the end of the talk. Okay, so the first work I show you, it was like control experiments on a fixed training dataset, synthetic dataset, to understand the mechanism of knowledge acquisition. But what happened if you take like a large language model that is trained on command crawl, the total web, Wikipedia, etc., and you want to add some specific knowledge? It can be like very interesting because, for example, we have like a data set, and we say that we want the model be specialized in some stuff, like for example LATAM culture or maybe medical stuff. Is it like how many data you need, and how the model will behave with this new data? So they build also a fictional dataset about government in Mars, and they inject this dataset into a large language model during pre-training. So the dataset like is a collection about fictive worlds, so they took real events into Wikipedia and they replaced the entity, the names, the date, etc. by fictional ones. And in this data set, they evaluate like the memorization probe. So how we can reconstruct some fact based on the context. So we measure the probability given the context, and we observe the evolution during pre-training. So you have like this kind of curves. So you have like the probability that increase when you inject the knowledge. The injected knowledge is here, just here. And when you inject the knowledge, it will become higher. But what we saw as well is that after some step, the probability will decrease. So it means that the model tend to forget the knowledge that was injected. So they did like a lot of experiments. So they tried different strategy to inject this new knowledge at different pre-training stage. For example, what happened if we inject this knowledge like the first data that the large language model will see? What happened if it's at the end of the training? They test a lot of that. They varying model size, for example, 1 billion versus 7 billion. And they did all this experiment. So what they, the first result they show is that, so at each time you inject new knowledge, the probability smallly like increase during time. So each dot is an injection. And if you inject like the same data at every time step, so the memorization will be better, but the semantic understanding of the knowledge is not that good, and the model forgot faster this knowledge than if you do semantic injection. So semantic injection is paraphrasing the data, so you augment the data like in the previous experiment. So if you duplicate, you have better memorization, but it forgot faster. And if you paraphrase, you have a good memorization, and the memorization and the semantic understanding of the knowledge are similar. And if you have like just one-time injection, so if you think that just giving one time the knowledge into the large language model is sufficient, it's absolutely not. So the probability is very low. But I have a question for those who know good LLMs, is why data poisoning and trigger works so well. So if you don't, I will talk about it later, but data poisoning is like, for example, I have a blog post in my webpage, and I will know that large language model will scrap my blog post, and I will put like 3 words in Latin, for example, like I don't know, 3 words in Latin that are really rare in the data, to change the model behavior, to hack him. And it's like very, very powerful technique. So if you have the answer, I have it, but it's a small test for you. Let me know. Okay, so the first key results are that in LLM, knowledge is acquired by a small step. You cannot inject just one-time knowledge and hope that the model will learn like perfectly this knowledge. Is not possible. You will have to inject a lot of time during training and be careful about forgetting the dynamics. So what is like very difficult with low and long entity knowledge is that when you have new data and you don't see this data, it will forget. So this is results about the training stage. So maybe is it better to inject the new knowledge at the beginning of the training, at the middle of the training, or the end of the training? Well, it's the same, but you will have like, of course, better memorization if you use bigger model. Of course, we saw that in the first work, because when you add the number of parameters, you add the knowledge storage capacity. So inject knowledge at a later stage does not improve acquisition, surprisingly, because you expect that large language model learn like the syntax, the language in the beginning of the training, and after it will learn like knowledge on some specific facts. But they found that like this is similar to inject knowledge at the end or in the beginning of training. So after that, they start to study like the forgetting dynamic. So how quickly is the actual knowledge lost? So they measure it, like for example, if you have like very high probability when you inject the knowledge and very low probability after this step, this is this ratio. So if it's 1, it's completely maintained the knowledge. If it's 0, it forgot everything. So they find like with simple duplication, like if you put like the same sentence at each injection, it will forget faster. And also there is like an interesting finding with the batch size. So if you increase the batch size, the model tend to forget, to less forget the new knowledge. So you need like big batch size for training LLM. And so the key results are that the forgetting is faster if you don't have diversity in your data. So it's very important to transform your data at each training step, because otherwise it will forget this knowledge. So the conclusion of this work is that there is a learnability threshold for facts. So if you don't see a fact for a certain amount of step, the large language model will forget it completely. And the popularity determines the acquisition speed. So popular entities are really well acquired by the model, but we saw like with one-time injection that rare entities are really hard to acquire, and that diversity, like in the first work, is very important and central for knowledge acquisition. So what's next? How to better inject knowledge in LLMs? Well, it's my postdoc subject, so I don't have a lot of clue for now. But like the scientific bottleneck on a large language model is that we have like the proof that large language model struggle to acquire long tail and rare knowledge. And that when you force the integration of new knowledge, for example, if I want to specialize my model in some medical stuff, in LATAM culture, for example, it's very hard because it will lose its older capacity. So it's a very interesting experiment to do. For example, you have like performance on European culture. You specialize your model on LATAM culture. And what is the performance of the LLM on European culture after the specialization? Well, the literature say it will decrease because it will forget the old knowledge. And for now, like all the work that I saw say that retrieval augmented generation, RAG, are always better than fine-tuning the models for long tail knowledge. So this work was like comparison between fine-tuning and retrieval, and they like show in a lot of settings that RAG, so RAG is the connection to an external database, is like 2 times better than every fine-tuning process. So it's a big problem because sometimes you cannot have access to RAG, you cannot access to web search. So it's a real problem to find a way to encode specific knowledge into the parameters of the LLM. Well, that's it. Thank you for listening. And if you have any questions. Yes?
At the end, you said that the RAG is better than the fine-tuning. Is it only for those specifications or for the overall performance of the model? Like specifically on the Latin, or is it also on the European culture, for instance?
It's always better for knowledge in general. For example, fine-tuning, we use only fine-tuning to, for example, change the model behavior. For example, if you want a reasoning model or something like this. But for new knowledge, it's always better to have RAG because you will like search into a fixed database. So if the knowledge is in the database, you will retrieve it, and it's, of course, way better than parameterization.
I don't know if it is a question, but I think that we are trying to break something that is part of how we train machine learning. That is that we are computing the error across the whole data set or across the batches. No? So maybe that makes sense why the size of a batch is important.
Yeah.
So maybe the solution would be to change the loss function, no? Like, because we are telling the model, okay, minimize the overall error, so isolated knowledge will always be in the long tail, so they will have less contribution to the total error, and that is
Yes.
why. So I don't know if you have seen that maybe there is an opportunity to look at that like it's to changing the statistic prior on top of which we are learning, no?
Yeah, exactly. It can be like a very powerful solution. Actually, when they train Gapron, so the LLM of INRIA, they try a lot of loss function, and they found that like this loss function work with really small models, but when you use like bigger model, it tends to be similar. And the intuition is that when you don't have a lot of information, maybe changing the loss will optimize better, but in a very big quantity of data, for example, next token prediction is maybe more difficult to do it, because next token prediction, how do you know like that the next token is rare fact or popular fact? You know, it's very, I think, very difficult to do it in pre-training, but I think also it can be a promising solution. I didn't see a lot of work on that, but definitely into the optimization, it can be a way to overcome this problem.
Yes, and then there is well, that is something we will need to like rethink, because it is not only that the next token, if it is popular or not, but in general, it's like, am I learning from a specific kind of knowledge that is less common or not? But then I always think of how we learn, no? And it's true that as you were presenting, you had like a phase in which we just learned to speak, not to reason, no? I mean, I don't know if it is like this or not. And then we are able, using language, among other cognitive tools, to reason, no? And that is why we have phases in learning, which is just speak, and then, I mean, probably everything happens in parallel. So maybe, I don't know, there is like a side opportunity of work there on how we structure these different levels.
Yes.
Because at the end, the brain is not homogeneous also, no? So it would be, maybe it's an interesting conversation with cognitive science people and all of that. Changing the scope, how do you see the future of the work we are doing on how to, let's say, inject this knowledge? It's more around the working in like a let's say, in an inference mode, the scenario in which like RAG-based approach or something like that, or?
So for me, my intuition, but it's strongly biased by my background in graph. So for me, when you learn knowledge, you learn structure of knowledge. For example, when I said that I did my PhD in CNAM, well, the LLM is capable of rely like me with CNAM, and he knows that CNAM is a university, that university is a place where we learn some fact. So there is like a hidden structure inside the knowledge, like the syntax of a language. So for me, my intuition is that if you give it explicitly the structure during learning, maybe it will learn faster, it will better acquire this knowledge. So that's the core of my experiments now. So it's giving like explicitly the knowledge structure instead of force him to learn it. So I have confidence in knowledge graphs because it's my background, but maybe it will not work. We will see that.
So, but so your idea is to, let's say, at pre-training or supervised fine-tuning time, to use, let's say, to include the structure, the graph into this phase.
Yes.
Yeah, I mean, it's interesting actually, again, because we also learn to create these knowledge graphs, this connection. So if we, the way I see this is like we are teaching a baby, no? So it's like if you teach the baby to understand some forms of knowledge like graphs in which things are related, so probably we can hypothesize that it will use this in a different time, no?
Yeah, exactly. And multi-hop reasoning, like I'm relied to INRIA, which is laboratory, which is in France. Like this multi-hop reasoning is the base of knowledge. So for me, there is maybe it's a promising direction to learn.
Okay, thanks. I don't know if I'm hijacking the whole.
Questions online? Do we have questions online? No? Okay, so more questions? Go ahead.
Thanks for the applause. No, I mean, it's okay. We are working together, so we have a lot to talk.
Exactly.
And don't want to. I think this is really interesting. It would be awesome to get into a place that we have discussed this many times, in which we can create like a sort of knowledge package of a specific domain. Right now, we are experimenting in the, let's say, socio-cultural aspect, because it's well, how we started, but eventually we would say, okay, everything you need to know to pilot an airplane is this, no?
Exactly.
So train on this and get back as an expert. So it would be really cool to have this, and probably, I mean, we have to explore a lot of options of doing it at, let's say, at training time, or by, let's say, by changing the weights, or by inserting things in the context. And it's a very appealing area, no? And it's also connected to other stuff we want to do, to do this in a frugal way, not to waste a lot of resources on small models and all of that. Awesome, thanks.
Exactly.
Thank you, everybody. So thank you so much, Yannis. I want you to ask you to give just an applause to Yannis.
Thank you.
And to the people online, just get connected if you have more questions. And you want to send the questions, just please do it, and we will come back to you through Yannis with the answers. So thank you so much, and wait for you for the next INRIA Chile Talk. Thank you.